Welcome to a lesson with Dr. Powell. Let's take a look at how our interpretation of a matrix like this as a scalar, x, can be beneficial. Specifically, what if we want to raise this to a power like to the fifth power? And we want to do so quickly using another technique instead of just multiplying this matrix over and over again 5 times. In fact, the same technique that we discussed can be used to quickly determine what this matrix is to a high power. Okay, a higher power than 5. But let's take a look at this case when we're raising it to the fifth power. We want to know what it's going to be equal to. So to do so, first of all, we're going to find a polynomial scalar that behaves like 0, like acting by 0. Now to do that, what we do is we think, okay, we know that the action of x can be described by this on a vector, right? Because x is like a scalar, so x times a vector, like 1, 2, what would that be? The result's going to be x times 1 and x times 2. Well, that's the same thing as thinking about what this does, right? If you put a vector 1, 2 in it, that's exactly what happens. But we also want the action of x to be the same as this matrix acting on the vector. So we want 1, 1, 1, 3 times 1, 2 to also be equal to the same thing. So this would simply be 3 and 7. Okay, so 3, 7. So we want 3, 7 to be the same as x, 2x. All right, so that kind of condition. Well, thinking about a 0 matrix, we know these matrices behave the same. So that means if you subtract them, the subtraction should behave like 0, like the 0 matrix. It should at least behave like it when we put column vectors into it. So why don't we take this and minus that? So we have x minus 1. So down the diagonal, we have like x minus 1 and x minus 3 down the diagonal, and then 0 minus 1, 0 minus 1. Okay, so looking at this vector, so this matrix. So this matrix represents, as an action on column vectors, should represent a 0 action of like multiplication by 0. Now, it does take a little bit of work to show, but intuitively, we could guess perhaps that the determinant of this matrix will behave like 0 as well, just written as a polynomial, right? So, and it does turn out there like that. I'm not going to withhold the description of that right here in this video, but we're going to take it for granted that if we take the determinant of something that represents the 0 matrix, we actually get something that behaves like 0. It kind of should make sense. But what could go awry is that this is, at least in terms of entries, is not equal to 0, 0 if you equate entries. Like x minus 1 right here is not 0 right there. Those two things are very different. However, what is the same, and what we can say is the same between these two guys, is the columns. So the 0 column here is actually equal. This is actually the 0 vector. That's the 0 vector. So we're equating. So this description of equivalences has to do with columns, not with individual entries, because now determinants often focus on what's happening between individual entries. Because of that, well, there's a little bit of work to be shown that the determinant will actually match the determinant of this in this case. So, but we'll take it for granted for now that we take the determinant of this guy, we're going to get a scalar that's 0, that behaves like 0 if you apply it to a vector. So let's do that. Take the determinant of this, x minus 1 times x minus 3 and FOIL that, we have x squared middle, and so we have negative x and minus 3x be negative 4x, and you have a plus 3. Okay, so that's that, and then you subtract going this way, so you end up getting a minus 1. So you end up getting x squared minus 4x plus 2. Okay, this is the determinant of this zero matrix action, and we call it the characteristic polynomial of our matrix here, 1, 1, 1, 3. This is the characteristic polynomial, and we know it's going to behave like 0. So if we like multiply this polynomial to any vector as a scalar, it'll automatically make that vector 0, to be at least the output of it 0 of that process. How can you use this now to raise a matrix to a high power? Well, let's think for a minute. What we're going to do is think about like x to the 5th. That's really what we're after, because we're after the matrix to the 5th power. But you know, every time you have a clump of x squared minus 4x plus 2, that's equal to 0. Now, when you do polynomial division, like x to the 5th is equal to x squared minus 4x plus 2 times something plus a remainder. So if you divide this into that, what you get is you get what would go right here, the quotient, some quotient multiplied by this plus the remainder. Now, if this guy is 0, then that means this whole part is knocked out of the water, and all you're left with is the remainder. In other words, x to the 5th is actually equal to the remainder in this polynomial division process if we're thinking about x as being a matrix and what we can do with it there. So really, all we have to do to find x to the 5th now is to do polynomial division and discover what that remainder is. Now, and then interpret that as a matrix. This remainder will have degree, so it means the highest exponent in this remainder, degree less than what you see here in the divisor. See a 2. So that means the remainder has to be up to degree 1. That's really nice. So it's like, so some a times x to the 1 plus b. That's what the remainder is going to look like. And that'll actually tell us exactly what x to the 5th is. Now, remember that these are kind of like actions. Like this is like a scalar action. Remember what a scalar action is like? It's like a diagonal matrix like B, right? So this B represents a diagonal matrix like this because that's how B acts as a scalar. If you're multiplying B to both components of something, like if you have like a vector like 2 and 3, say, B multiplies to both parts, that's the same thing as acting like this. Okay, we could just have A multiplied to the matrix X. So 1, 1, 1, 3. So this right here, for some A and B, is going to give us x to the 5th. We just have to figure out what that ax plus b is. All right. So we do a little polynomial division to discover what that should be. Now, you can reference, I have another video on this that you can reference. But the way I'm going to do this polynomial division is by generalized synthetic division. So it's a step up from synthetic, but it makes polynomial long division faster. So it isn't synthetic division as you might see in other contexts, but it works amazingly well. What we do is we take what we're dividing into x to the 5th and think about it in terms of its coefficients, like 1 times x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x plus 0. All right, so that's what we're dividing into. Now, what are we dividing by? Well, x squared minus 4x plus 2. But we take the part that's after the leading term, and at least the way I'm describing it, works when this leading coefficient is 1. But notice I can use higher degrees. That's what generalizes it. I can use higher degrees here, but I am going to, again, require that the leading coefficient at least is 1. Leading degree, doesn't have to be, but this I'll say is 1. Okay, then what do you do with these other guys that trail after? Well, you change the sign and you write them down right here. So 4, -2. Okay, just took these, change the sign right there. And then we proceed as usual, but almost. We need to mark off where the remainder is going to be. Since there's 2 things here, the remainder will take up 2 slots. So I just put out the remainder will be represented by 2 different things. So then I proceed. I just drop a 1 and take 1 and multiply to this. Now, how do I put this up here? Well, 1 times 4 will just go in the normal position where you would normally think for synthetic. And then this guy will be one more spot later, but just on this row down here. So 1 times -2 would be -2. It's like 1 times 4 -2 is 4 -2, but written as a diagonal like this. Then you add down 4. Then 4 times 4 -2 would be 16 -8, written that way. Then we add, and we get 14. Then we say 14 times 4 -2, which would be 56, and let's see, 56 and -28. Then we add right here, and we end up getting 48. Okay, and then we have one more big multiplication to make. So 48 times 4 is, let's see, 100, 160 and 32, so 192. Oh, hold on. Nope. Yeah, 192 is 30, 32. And okay. So then, and then we have 48 times -2, which would be -96. And then we add down right here. And we end up getting, okay, so then we add right here and we end up getting 164. And then adding down here, we get -96. Okay, and great. Now all we're interested in is this remainder. Now this remainder can be thought of as 164x minus 96. So that tells us right here that to find x to the 5th, we could say 164 times our matrix, 1, 1, 1, 3, and then we can say minus 96, thought of as a matrix, is 96, 96, down as a diagonal like that. Okay, so that's what x to the 5th is. Now, it is true, maybe it would have been less work to just multiply this out for x to the 5th. However, this is an interesting process, and for some matrices, it's faster doing it this way. But it gives a lot of insight into how we can work with matrices, and a lot of things we can do with them are based upon this idea that we can relate things to polynomials in such a way. So this is a good example of this. Okay, so proceeding, we can perform this computation, and we end up getting 68 at the top here. And then we have 164, and see, 164 times 3 would give us 492, and then we subtract off 96, and we'll end up with 396. Aha, we just took this matrix and raised it to the 5th power, and that's what we got right there. Thanks for watching.